Hello once again, and welcome back to Database Management Systems. This video is in continuation of the previous video where I talked about Armstrong's axioms and proved the union and decomposition rules. In this video, I'm going to prove the pseudo-transitivity rule, and then we'll go ahead and talk about canonical covers and how to calculate them. So let's first begin with the pseudo-transitivity rule. This rule is fairly simple to prove, and I'll show you how in a minute. Let's just read the rule first. It says that if A determines B holds and C determines D holds, then you can say that AC determines D holds. Now, in this case, all we have done is, because we are trying to say that A determines B, we're trying to replace B with A in this functional dependency. So this B is simply replaced with A. And that's all we need to show by proving it. We are given two things and we have to prove a third thing. So the first step, as usual, is going to be writing what I already have, which is A determines B, and we can write that this is given. As a second step, I'm going to write CB determines D, which also is given to us. And then as a third step, I'm going to apply the augmentation rule in step 1 and make it look like AC determines BC. So you can see here and here I have added C on both the sides, and this is augmentation of C in number 1. Now, as a fourth step, using these things that are available, I can see here that this is BC and this is also BC. So this means, once again, like the previous two rules, I can apply the transitivity rule and make it AC determines D, because there is this BC present here and BC present here, which means I can make it AC determines D. And I'm going to write next to it that this is the transitivity rule applied on 2 and 3. And that's it. That's your proof right there of AC determines D. That is how pseudo-transitivity can be proven. And that's where we are going to stop proving Armstrong's axioms and start using them in calculating canonical covers. So first, let's see what a canonical cover is. So let's talk about canonical cover, or it is also sometimes called an irreducible set of functional dependencies. It is a simplified and reduced version of a given set of functional dependencies. So if you are given, say, 10 dependencies, you can reduce them and convert them into 5 dependencies by applying the Armstrong's axioms. And we are going to see that with an example. So consider that you are given a relation R which contains columns A, B, and C, attributes A, B, and C, and the set F of functional dependencies given to you is right here. So what you can see here are all the functional dependencies given, which are A determines BC, B determines C, A determines B, and also AB determines C. These are the 4 dependencies which are given to you. And now from these 4, we are going to try to reduce them because there are dependencies which are kind of duplicate ones, which you do not need, which you can derive from the existing dependencies. So we can remove those and reduce the set so that our normalization process, which you're going to study later, will become much more efficient. So let's start by, first of all, applying the simple decomposition rule on all these dependencies. The decomposition rule is a very simple rule to apply. So all you need to do is wherever you see more than one attribute on the right-hand side, you just need to decompose it, which means I will be having A determines B, A determines C, and the rest of the dependencies I'm going to write down just as they are here. And after that, you can already see some of the things are already uh, reduced. For example, you can see that A determines B is coming here and A determines B is also appearing here. So you can remove one of those. And I'm going to remove the second one, which now reduces my set of dependencies and makes it A determines B, A determines C, B determines C, and AB determines C. Now, at this point, I can apply the transitivity rule over here, as you can see. Because I have A determines B and I have B determines C, and here there's a B and here there's a B, I can actually generate A determines C using these two. So I do not require this dependency since it can be generated by using the other two. So I'm going to go ahead and remove that. And it gives me A determines B, B determines C, and AB determines C. So these are the three dependencies left now. Now, with a bit of extra work, you can still eliminate one more, and I'm going to show you how. So let's take the dependency B determines C. We could augment over here A on both the sides, which gives me AB determines AC. And then obviously, so this is a simple augmentation. So this is augmentation of A in B determines C. So once I've done this, I can get AB determines AC. And due to this, I can further decompose this. I can decompose this now and make it AB determines A and AB determines C, which means by just using B determines C, I can generate AB determines C, which is the dependency present here. So this one is also not necessary, which reduces my set and makes it A determines B and A determines C. So you see, now you understand what I was talking about. Using just these two dependencies, we can derive all the remaining ones. So this whole set is actually equal to this whole set. And when there are less dependencies, we can perform our normalization process in a much more efficient manner. So this is how you can calculate a canonical cover for some set of functional dependencies. It is also known as irreducible set of functional dependencies. And after this, I'm going to show you a little bit of a shortcut to perform the same type of calculation, where we are going to see some rules, because this calculation is fine if there's a small set of functional dependencies. But if you have a really large set, you cannot really think clearly and reduce the set. So you cannot always know which rule to apply and when to apply to reduce the set. And therefore, there are some rules that have been generated on the basis of Armstrong's axioms, which we studied earlier. And based on those rules, we can perform we can do this calculation of canonical cover very easily without having to worry about which rule to apply when. And also at the same time, if you want to program a system to calculate canonical cover, even that is much easier by using these two rules. These rules are known as rules for extraneous attributes. An attribute which is present in your functional dependency is said to be extraneous if you can remove the attribute without changing the closure of the set of functional dependencies. Which means if I have a dependency like AB determines CD, then I can remove B from this whole dependency if by removing B, I am not changing the closure of these functional dependencies. And also, I can remove something from the right side, for example, D, if by removing that, the closure of the functional dependencies does not change. And you will come to know what the closure of a set of functional dependencies is when we do a small example for this thing, for extraneous attributes, for finding them and removing them. Now, the two rules that I was talking about are these. If you consider a database which contains functional dependencies, A determines B, which contains a functional dependency, A determines B. Now, we're not talking about a database, it's one table. So for one table, there's a dependency, A determines B. Now, in this, consider an attribute which is small a that you can see right here, the small a attribute. So the small a attribute is present, and let's say that this attribute I can subtract from the given set, which is set A. So I'm subtracting this small a attribute from set A. And after doing that, I'm just writing the dependency as it is. I'm just removing one attribute from the left side and writing the dependency as it is. Now, if this can logically imply that F, which is a set of all the functional dependencies from which I am removing the original dependency, which is A determines B, I'm removing that dependency. And then performing a union of that with a new dependency where I have removed one attribute from A determines B from the left side. So if this logically implies F, which was the original set of dependencies. So if you can derive the original set of dependencies even after removing one attribute from A determines B on the left side, then that attribute small a is an extra attribute and we can remove it. And then the second rule is about the right side. So this time we are saying that small a is some extra attribute in B, which is on the right hand side. So you can say that small a belongs to B, and there is a set of functional dependencies. So here you can say F minus A determines B. So I'm removing once again the original dependency from here. The original dependency is removed and a new dependency is added where from the right hand side I am removing this small a extra attribute. Now after doing this, if the set of dependencies that I have logically imply F, which was my original set, which means I can get all my original functional dependencies back even after changing this functional dependency. Then you can say this small a is an extraneous attribute and you can let go of it. So these are the rules, and in the next video I'll be telling you how these can be applied on a set of functional dependencies by calculating an example. So stay tuned for that, and thank you for watching.